Okay, now we're going to talk about colligative properties. Now I hope you've learned in class exactly what colligative properties are. They are properties that depend on the amount of particles present. So before I dive in to show you quite a bit more about how to use colligative properties to understand chemistry a little bit better, I wanted to set up a little demonstration for you so that you could see the colligative properties in action. So we have here, I'm going to particularly talk about two different colligative properties: increasing boiling point and lowering the freezing point. So we've got some water here that I'm getting ready to heat up so that it will start boiling. And I've got some ice here that I'm going to allow to melt. But you remember that if we add a solute, to the water, it's going to affect the boiling point and it's going to affect the melting point. And I'm hoping that you've learned that if we add a solute to a solution of water, that it's going to increase the boiling point. So we should expect to see an increased boiling point when there's solute present, and it's going to decrease the melting point. I've got two different solutes here. We've got salt and we've got sugar. So we're going to see how does salt affect the boiling point and how does sugar affect the boiling point as well as the melting points. And in just a few minutes, after I have this all set up for you all, I'll walk you through exactly how we know which one should have a larger effect. And then afterwards, I'll be able to show you what actually happened. So it would be best if I did some math and calculated out exactly the same concentration, but I'm just going to eyeball it. I put 225 mils of water in each of these. One's labeled water, the other one is labeled salt, so I'm just going to pour some salt into this one. Just kind of eyeball it. I want to put definitely enough that we'll see an effect. So that seems good. And then the sugar one, we'll go ahead and pour some sugar in there. Again, I'm just kind of eyeballing it. And then we have the beakers here of sugar, of ice, and so in one of them I'm going to pour some sugar in there. We're going to see how that affects the melting point. And I want to get quite a bit because I want to see some drastic results. And the other one we're going to get some salt. Okay. So it'd be best if I measured it out and did some math to figure out molarity, but for this demonstration, I think that this should be good enough. So what I'm going to do now is start heating up the water. And this is already starting to melt, so we're good there, and we'll have to see what happens. So while we're waiting for the ice to melt and we're waiting for the water to boil, let's have a look at the concepts behind colligative properties so we can see exactly why those things are going to happen, and then we're also going to look into why we might end up with different temperatures in our salt solutions versus our sugar solutions versus our tap water, which is as close as we're going to get in this case to pure water. But we know tap water is not actually pure, but compared to all of the solute that I put in the others, it's going to be a lot better. So there are 4 colligative properties. And a colligative property refers to anything that changes based on the number of solute particles present. Now remember, solute refers to the substance that is dissolved in the solution, and we're usually referring to water. So if there's more or if there's something dissolved in the water, it's going to affect its boiling point, and its vapor pressure, and its freezing point, and the osmotic pressure. So it depends on the number of solute particles. The more solute particles present, the bigger the effect. So you went through these in your notes and you wrote down some things about them, but you need to know that when something is dissolved in the water, it's going to cause the vapor pressure to decrease. It's going to cause the boiling point to increase. It's going to cause the freezing point to decrease. And it's going to change the osmotic pressure. This one you really just need to know basically by definition. So these two, I think, are the easiest to understand, especially this one. So I'm going to talk about this one here. The reason is because when the solutes dissolve, they form a much stronger intermolecular force than the water or the solvent by itself, making the solvent want to be in that phase longer. I am going to show you one thing here that I'll erase when I'm done because I want to work through these examples. But let's talk about water by itself, okay? So pure water versus salt water. This is going to kind of help you memorize 2 of the 4 colligative properties. This one you just need to know is one, and then this one you just need to memorize that. Vapor pressure lowers. But these two, this is going to help you remember these two. So if you have pure water, here's like the phases. We've got solid, we've got liquid, we've got gas. And if you remember, it turns from a solid to a liquid at 0 degrees, and it turns from a liquid to a gas at 100. Now let's look at it when it is salt water. So when it's salt water, the melting point is going to lower. So maybe it would be around -3. And the boiling point would increase, maybe up to 103. We're actually going to see in just a second what it actually does. So solid, liquid, and gas. Do you see that both changes made the liquid phase bigger? When it has a solute dissolved in the solvent, it forms a really strong IMF, making it so that the liquid phase wants to be present as long as possible. It extends the liquid phase in both directions because of that extremely strong intermolecular force between the solute and the solvent, which is much stronger than the intermolecular forces with just the solvent by itself. So that's why it is, but that might help you remember. It's going to make the liquid phase longer by decreasing the melting freezing point and increasing the boiling point. Now, the second thing that you're going to need to know, so you would need to know that you need to memorize these 4. You need to know that it depends on the solute particles. The other thing is I might actually give you some solute particles, and you're going to have to figure out what has the most effect, the largest effect on the boiling point or the melting point. Which one will change it by the most? Now remember, it depends on the number of solute particles. What you need to do is you need to think about what are these substances doing in solution. Are they the electrolytes where they split apart, they break apart into their ions? Or are they non-electrolytes that do not? How do we answer that? Remember, electrolytes are ionic, acids, and bases. Ionic is a metal with a nonmetal. That's a very basic definition with their exceptions. Acids are things that starts with H. Now again, it's also a more basic definition, but it'll work. And bases are things that end in OH. You are going to get better definitions for these when we get to the acid-base unit, the acid-base half of this unit. But for now, you're looking for metal with nonmetal. You're looking for you're looking for H plus at the beginning, or you're looking for OH at the end, but be careful with the OHs at the end because it does have to be OH attached to a metal or a polyatomic ion. If you don't see one of those two, it is not going to be a base, it's actually going to be covalent. Non-electrolytes are covalent, and they do not break apart into their solution, into their ions. Covalent compounds, technically acids are covalent, so it's covalent compounds other than acids. So let's look through this list. What is NaCl? That's a metal with a nonmetal. That's ionic. So this one is an electrolyte. C6H12O6, that's glucose. Non-metal, non-metal, non-metal. We don't see any polyatomic ions here. This is covalent. That one's not going to split up. We have a metal with a non-metal. That's ionic. This one's going to break apart into its ions. H2SO4, this is sulfuric acid. So this is an acid. So if you look, we've got 3 electrolytes, and we have this one right here that's a non-electrolyte. Let's see what they actually do when in solution. So if it's covalent, let's start with that one. If it's covalent, it is not going to break apart. So it's going to go from solid sugar to sugar dissolved, because sugar does dissolve in water. Woohoo, I'm glad, because we've got soda, and we've got Kool-Aid, and we've got sweet tea. If it weren't for those things, if it weren't for sugar dissolving, we wouldn't have those things. But do you see what it looks like on opposite sides? The only thing that's changed, it's gone from a solid to aqueous, but it is not broken apart into its pieces. So how many particles do we have on the product side? That's the number of coefficients. We have 1. Now let's go through and do all of our electrolytes. NaCl is an electrolyte, so it's going to break apart into Na plus and Cl minus. There are 2 particles over here. The more particles, the larger effect. So which one's going to affect the boiling point the most? Definitely this one. Which one is going to lower the freezing point the most? Definitely this one, of these 2. So in my demo that I set up for you, we tested out salt, trying to melt water with salt in it, and trying to melt ice with sugar in it. Now we see that this one should have the lower temperature of the 2. We'll find that out at the end of this. Okay, so let's do this one. Okay, this is also ionic, so it's also an electrolyte. It's going to break apart into its ions. Aluminum has a 3+ charge. And do you remember what happens to that 3? Yep, goes to the front. Don't forget about that. We learned about that in the reactions unit. 3F minus aqueous. So if you look, that's 1, 2, 3, 4. This is 4 particles. Oh, even more. So AlF3 is going to have even a larger effect than NaCl. The more particles, the bigger the boiling point, the lower the freezing point, the lower the vapor pressure. So the more particles, the bigger effect. Let's do our last one, H2SO4. The 2 is going to go to the front. This is an electrolyte. 2 is going to go to the front. And do you remember, are we supposed to break apart this SO4? Do we ever break apart polyatomic ions? Are we allowed to mess with them? The answer is no. So we're going to see SO4, 2 minus aqueous. Now let's count our particles. 1, 2, 3. So the question would be, which one has the largest effect? What you need to do is cross off your non-electrolytes first. So cross those off, because those will not be your answers. And then of all the ionic ones, of all the acids left, of all the electrolytes, you need to figure out which one would have the most particles, and in this case, it would be AlF3. So here would be our answer. AlF3 would have the highest effect. Right, highest instead. Highest effect. Or most affected. Why? Because it has the most particles. So, there you have it, colligative properties. Now, I'm going to show you what's happened to our demo. Let's see if we really do end up with a higher boiling point temperature for the salt than the sugar. But both of these should have a higher boiling point than the water by itself, because both do have solute particles. Can't wait to find out. Okay, so now that you've had a chance to learn about colligative properties, let's have a look back at my demo and see how sugar and salt have actually affected the boiling points and melting points. You remember, the solute added, the more particles present, means the higher the boiling point, Let's look at these. Now, do you remember sugar and salt? Sugar is a non-electrolyte. That means it's going to have fewer particles per mole because it does not break apart into its ions. Whereas salt does. It is an electrolyte, so it breaks apart. So if you have NaCl, it's actually going to break apart into Na plus, Cl minus, meaning twice as many particles. So we should see, and I'm hoping we see it, we should see that the water by itself is going to have the lowest boiling point, then the sugar, then the salt. Okay, let's have a look. So here's the water by itself. Oh, wow. Okay, its boiling point is 99. That's pretty typical. It's usually pretty common for you to see something just below 100. So we're starting with water at 99. And I'm going to rinse off my thermometer between all my measurings. Okay, let's check the sugar. If this worked out, it should be higher than 99. Now, typically this demo doesn't have that big drastic differences between them, but let's see if there's a difference at all. Okay, here comes the sugar water. We're expecting to see one that is higher than 99. Yep, and we're looking at right at 100. Good, good. So we can see not a huge difference, but it is boiling at a higher temperature. Okay, now since salt is ionic, it's an electrolyte, it breaks apart into its ions, we should be seeing a higher boiling temperature. Let's see if we see something different here. So when I measure the salt, okay, let's see, we should be seeing one higher than 100. Oh yeah, and we're seeing 104, 104 degrees. That's actually a pretty big difference considering usually I don't see that big of a difference in the boiling points. It's usually the melting points where I see some bigger differences. So there we go, the water boiled at 99. When we added the sugar, it did increase the boiling point by a little bit. Then we had the salt. The salt's an electrolyte, so it increases the boiling point even more. So two things you're supposed to learn from this. The first is that if you add a solute to the water, dissolve something in the water, it's going to increase the boiling point. Second thing, if the solute you add is an electrolyte, it's going to increase it by even more. Okay, so let's have a look now at the ice, the melting. Now, first of all, before I actually show you anything, I want you to look at the ice. When you see the ice by itself, we see some melting. But look at that compared to the sugar. Do you see how the sugar is melting a lot more? Yeah, and then let's compare it to the salt. This is melting even more, even more. Why? Because we lowered the melting point when we added the salt, allowing it to become a liquid at a colder temperature. This right here is the reason why we put salt on our roads in the winter. So now let's get the temperatures. We are looking at, for the water, just by itself, I would guess this to be actually a little higher than 0 because I'm actually measuring the liquid here, not the ice. So I'm anticipating this being a little bit higher than 0. Yeah, and we're looking at 3 degrees. That's pretty typical. That's what's to be expected. So 3 degrees for the ice by itself, no solute. Now, if you remember, when we add a solute, it lowers the melting point. So we should be seeing something lower than 3. Let's go ahead and see what we're looking at right here, something lower than 3. Because there is a solute in here, so it should get down to lower than 3. Ah, yep, we're looking at 1 degree. Typically when I do this demo, I typically like to see it under 0. So it's a little higher than what I like to see normally, but that's okay, it's called science. So do you see that when we had ice by itself, it melted, the liquid in the solution was at 3 degrees. When we did the sugar, it was at 1 degree Celsius. So yes, we were able to get that liquid to be a lot colder. Let's check the salt. I'm hoping for something pretty low here because remember, salt is an electrolyte, so it's going to freeze at an even lower temperature than the sugar. Because not only is it a solute, it's also an electrolyte. So let's have a look at this one. Okay, still going. Wow, -9. -9 degrees Celsius. Did you catch that? 3 degrees with no solute, 1 degree with a non-electrolyte solute, and -9 degrees Celsius with an electrolyte solute. So why? Because this has a lot more particles because it breaks apart into its ions. Something else that you can kind of see, and you can't see it as well, but usually I actually have frost forming on the outside of the beaker. This time for some reason I'm not. It's probably because it's sitting closer to the hot plate, so it is a little bit warmer right now, but typically I get some frost forming on the outside of the beaker. Why? That water's coming from the air. When it hits the cold beaker, not only does it condense, but it ultimately freezes because the water inside is actually much, much colder than the freezing point, causing the gas, the water vapor, to actually become a solid on the beaker. So I typically see that. We did not get to see that this time. But as you can see, when we added the solutes, it increased the boiling point, and if it was a non-electrolyte, it increased it less, but if it was an electrolyte, it increased it even more. When we were looking at the melting points, adding solute decreased the melting point. And ultimately, those two things combine together to make the liquid phase bigger. If we lower the melting point and we increase the boiling point, the liquid phase is going to be longer. And why? Because the interaction, the intermolecular force between the solute and the solvent is much stronger, causing it to want to be a liquid phase longer. So I hope you enjoyed this demo. Good luck with colligative properties.